Welcome back to Ox Tools. I'm Tom. So we've got an interesting buddy project today. A friend of mine at work, his wife is a bread maker, and she killed her kitchen mixer for mixing the bread dough. Anyway, it's kind of interesting in that he gave me a loaf of her bread, which was wonderful, and apparently it was sourdough, so people that make bread are probably familiar with this, but the starter that she uses dates back to the Civil War era, which is kind of cool, or at least I thought it was cool. But anyway, we're going to try to help my friend Will out by making a new gear. Now this is a KitchenAid mixer, and this is a known weakness in these mixers. My wife also is a bread maker, and she's killed this gear herself. Now the replacements are cheap on Amazon. They're in the $8 range. Okay, the gear we're making today is going to be considerably more valuable than $8. But the idea here is to use a different material to add some durability to the system. So let's check out the problem and then let's make a gear out of a better material, and hopefully it'll last and produce lots of loaves of bread that we can partake in. So let's check out the problem. All right, so here's our offending gear, and it's a plastic gear with an aluminum hub, and then you can see the injury there to the gear. So what happens is when they're mixing dough, it's a long mixing cycle. They have to knead the dough in the mixer with a dough hook to help develop the gluten in the dough. So what happens, I believe what happens is the viscosity or density of the dough goes up, so the load on the motor goes up. The motor seems to be okay handling it, but what happens is I believe the whole system heats up, and then the yield strength of this plastic gear material goes away. Now if you look carefully here, and I'm not sure you can see it, but in where the worm contacts, now this is a worm gear, so this is not what we call a full enveloping worm. This is basically a helical gear that we're running a worm gear against. Okay, and that's allowed, but it's not so sensitive on center distance, so manufacturing wise it makes it easier. But you can see the flank of this gear is yielded and distorted, and from being overloaded, and all it takes is one weak tooth goes, and Bob's your uncle, and it's a goner. Okay, now this is $8 or $9 from off Amazon, right? And because this one was so jacked up, I went ahead and bought one. There's a brand new one off Amazon for $9. Okay, and so that I could be reasonably confident that measurements I was taking off of the gear were going to be, the way we want them. Okay, I guess let's put it that way. So, it's an unmolested gear. Now, as part of that, I started thinking about it even harder, right? And I said, geez, it'd be really nice to have the worm that goes with that. So guess what? Jumped on eBay, and here is the worm. Okay, there's the worm, and it's a 3-start worm, 1, 2, 3, right? And that meshes up with this little monkey here. And now I can actually measure the center distance, and that's one of the first things we're going to do here is measure that center distance. And when I say center distance, what I mean is the distance from the center of this gear to the center line of this shaft here. Okay, and it looks like it's a little over 3/4, less than 7/8. Okay, or for our metric folks, it's 10, 20, 21 millimeters, 20 millimeters, something like that. Okay. All right. So anyway, that's the job. And we're going to make a new one of these, and we're going to make it out of a nice hard bronze, Ampco 18, or otherwise known as 954 bronze. So let's check it out. The first thing I made was this little holder here. Actually, I'm going to use the new gear on that. This little holder that's got a little pin on it that we can set the gear on, and the gear can spin on it with no play. So this pin is a known distance from the end of this. So what we want to do is zero the center line of this pin, okay, with the lathe DRO, and then we can just take a direct measurement here on the lathe. Now, how are we going to do that? Well, I got this little thing here, and what this is it's just a shaft that's had exactly half of the diameter machined away, and it's handy for stuff like this. We're just going to put it in there. So when that thing is vertical, okay, we know that that is the center line of the spindle. Okay, so what we're going to do, I'm going to come over here, and we're going to raise this tool up for a sec, like that. Let's go up a little higher. So what we're going to do is float that in. Like that, okay. So, and now what I'm going to do is, I think I'm going to zero the x-axis, okay. And then I'll come out here, and then what I'm going to do is I'm just going to come in at that known distance, which is 1/2 of an inch, right? Now, since we're measuring diameter on the DRO, okay, back up a little. I have to go double that. Okay, all right, and beep. Okay, so now the center line of the spindle is on the center line of that pin, theoretically. All right, let's get out of here now. Let's drop that back down. Let's get this out of here. And now what we can do is put this little monkey in here, our armature here. And one of the reasons I bought this armature is I was like, hey, maybe I can use that that worm and make a hob, make a hob out of it that we can cut the gear with, but it's too small and it's got some problems. So let's put a little. I got this little shaft collar, and I don't know about you guys, but I keep. Okay, that's good. All right, that still turns. All right, now what we want to do is I want to get that in mesh. Actually, you know what? I think I want that thing to turn freely. I don't want a bunch of friction on it, and the reason being, yeah, I want to. So basically, what I want to do is I want to feed that in there until my backlash goes to 0. Actually, come on, Mr. Wizard, keep your brain going there. Okay, all right, now we're locked in. All right. So, you know what? All right, so there's no wiggle there, but you know what? I got to be a little bit careful here because I have the old gear. And as I pointed out before, it's got evidence of where the worm was bearing on the tooth. So it might be smarter to put this gear on and then go into that same depth, and that would probably. See there's how it works. Go into that same depth and see what that number is in comparison to this one. So let me write that one down. So that's, yeah, 1, 6, 8, okay. All right, let's do that. Let me change it over and then we'll look at it again. All right, so I got the old one in here. And so what I did was I was able to, and this, I hope this doesn't blow the camera out. I was able to look up from underneath and see where the diameter of the worm is intersecting the marks left from the pressure, the overpressure on the plastic gear. So I got a number. I have a center distance number, and it's slightly more than running this all the way in until there's no place. They're actually pretty close. They're only a few thousandths apart. So, yeah, which one to use, right? That becomes the question. Since we're going to be making this out of a more durable material, my inclination, and I don't have the case to the mixer where I can take an accurate center distance measurement. This is just inferring that center distance from the pressure marks and backlash. This one's pretty good. There's no backlash there. This one at that same distance. Let's take that out. Put that back in. I don't want to squash it here. Let's see. Let's run into that same number. Oh no, it's okay. All right. It doesn't have any play. I thought it did. Oh yeah, it does. This is the tiniest bit. Okay, so that actually makes me feel pretty good. For manufacturing reasons, they want to be able to assemble this pretty easy, right? So looser tolerances are your friend. So loose tolerances assembled correctly make precision assemblies, right? And that's the ideal in manufacturing. Not always achievable, but in particular with gear meshes and stuff like that, they can get real fussy. So anyway, we're going to go with this number, and let's see, what is it? So that's 13/16, 0.8125 is the center distance that I get from the center line of the worm to the center line of the gear. So we're going to go with that. We're going to take some dimensions off of this so we can make some blanks and measure this helix angle here on the gear, right? Because we have a helix angle, oops, blurped. We have a helix angle that we have to deal with, okay? Measure that, we'll make a sketch, and we'll get cracking. All right, so I made a sketch of the gear here, okay, the gear blank, and so we'll make that out of this Amco 18. I think it's big enough. Yeah, it's big enough. So we'll prep the gear blanks, and then this is so I want to make a couple of gears. So I want to make one for my friend Will and one for my wife for the next time hers kills the gear, and then I have to go in there and replace it. I'll make a bronze gear for hers as well. So this is an arbor that I can put the gear on and then crank it down and take the gear blanks on and off and machine the gears. So this collects all the information here. Here's our worm center distance that we just did over on the lathe a little while ago. Let's see, what do I want to say? So now what we care about is this helix angle, right? Because we have to set this gear up at an angle in a dividing head to cut those teeth. So let's and this is a what do we want to call it? A field expedient. Is that the right word there? All right. So what I really want is I'd like to hold that in the vise or something, right? So I got the protractor on the face of the gear. Now these, just so you guys know, this is officially not quite correct in that these have a helix to them, okay? So, full disclosure, we're not cutting a helix in this particular case. We're going to cut a straight tooth. But it's so close to straight that I think we're going to be fine. And I can do this easily and get a. I'm just eyeballing. Let's see. Let's check it against the center line there. That looks pretty good. Maybe a little. Let's try that. Yeah, that looks pretty good. Okay, so what is that? That is 59. Okay, so what is it? I want the small angle. 10, 20, 30, 31 degrees. Okay, 31 degrees is our number. And that's should be the setting to tip the dividing head up to hold the gear blank and cut that tooth. Now I got to think about it a little bit, but let's get set up to cut some blanks, because that's really the next thing. Or actually, we'll make blanks and we'll make the arbor. I think that's the order of operations there. That way I can get the fit that I want between the gear blank and that shaft. And then we're just going to thread the end of it, and we're just going to clamp it to that shoulder nice and tight, and that should hold it enough for it's not really hobbing, but we're going to cut those gear teeth. Okay. Snug it down a little bit. All right, that's close enough for this particular thing. We're going to be cleaning the OD up anyway. Couple thou. All right, not going to fuss over that. So, yeah, let's see what tool we're going to use here. I like this tool for bronze here. It's a high positive. It leaves a good finish, and it cuts real freely. So, I'm going to face this first. This stuff machines really nice. It's real hard. Alright, let's get a 0 on that. And then I'm going to take just a whisker off of the OD to calibrate the tool. Okay, got a nice cleanup. And that's enough to get the micrometer on it. Okay, let's see what we got. And then, now that we got the tool calibrated, I'm going to get close to the OD. Let's do that. We're looking for 1.444 for our OD. That's good. Let's make sure this is tracking properly. Okay. All right. Now I'm gonna holage. And slow that down. Oop, wrong one. I'm not worried about center drilling this just yet because this drill is undersized, and I want to bore the ID so that it's nice and straight and concentric with the OD. I can drill the second one too while I'm here by going deep. See the chips break real nice here. Alright, that'll work. Pop in there and get a measurement. Okay, 1 thou big. I think I can live with that actually. Let's go ahead and just skim it off. 1 thou big. Just dust it off. Okay, so I'm going to leave these corner, actually not that corner, but this corner and that corner sharp, and actually this one can be, I got to think about it. Okay, time to let's get a nominal number. So I like using pins for this, but I want to know which 364. Okay, let's grab the 364 pin. All right, so let's see here. That's 364. Okay, that's. Now, heads up when you're doing this, I don't know if that's still in the boring bar is right behind me, so you got to be careful you don't pop it out and jab yourself on a. All right, so that's 363, right? Be sure to read your pins. 363, yes. Okay, 364. Okay. All right. All right. So 136. There, okay. All right, let's go back in. We want 375. We'll go to 370. Ooh. All right, it's 374, my favorite sound. All right, so we're, I don't know, half thou under or something like that. Let's, we're just going to run this through on the same setting. And a lot of times you got tool spring that takes another pass, or takes a little tiny skim cut. So we'll see how that works. Okay. Yep. See that fuzz? So that's the I don't know, spring pass, whatever the tool pressure. All right, there's the 375. And now that fits just the way I want. Watch this. All right, Mr. Wizard, don't stab yourself on the boring bar. Boink. Machinist, happy sound, right? Okay. Okay. I'm going to break a couple edges here, and then we'll part this monkey off. And that's well, it's got a second side we got to do too. I don't know if I've ever showed this particular trick here for picking up an accurate parting blade here. So what you do is you just put a test indicator against your parting blade very carefully. It doesn't really matter what you're set at, okay? These stupid indicators, man. Oh, God. You know, these exposures are always a pain in the you-know-what. I want to show you the indicator. I want to show you the whole setup. God dang it. How about this? Let's try this. Okay, let's turn that light off. You can probably see the needle. So what I'm going to do is I'm going to come up, I'm going to touch my work with the parting blade, but what I'm doing is I'm watching the indicator for any little movement. Right there. Okay. So now what I know is I know that that's calibrated against that surface. So I know the thickness of the parting blade in this case. I just measured it, 122. So dial off 122. All right, re-zero it. So now my the edge I care about in this case is zeroed. And I can just dial off the number on my drawing, which is 592. Now, prudence is such that you don't want to part off right on your number. You want to leave something there to finish, unless the tolerance is such that it doesn't matter. So we're going to go a few thousandths more. I don't know, 3 or 4, something like that, 5 maybe. Let's do 5, yeah, why not? And then we'll part this monkey off. Well, you can feel how tough this stuff is with the parting blade. It takes a fair amount of feed pressure to make it go. Alright, getting close. One gear blank. Okay, so I'm going to set that one aside and let it cool off. I'm going to make the second one off camera, just cause, and then we'll go from there. Massively over. Clean up so that I can get a measurement. Okay, yeah, this one's pretty close here. 5.9. Yeah, I probably should have left a little more on the part, but it's fine. It's still going to clean up. 5.97. So probe, what, 4/1000ths. Okay, take that to the bank, and let's do that. Okay, now there's a, I don't know if you guys noticed, but you see there's a little washer face, that's machined on there. It's about 15/1000ths. So we're gonna put that little chunky monkey in there, 15, and we're gonna do it from the outside in. Since my tool's already calibrated, 684, 9, 8, 7, 6, 84, and then we're going to come out. Okay. Couple of edges off. Okay. Now, I mentioned this earlier, but I want to leave that edge sharp, and you'll see why. You'll see why in a little while. When we cut the gear teeth, I need a good crisp edge to pick up off of. So that's going to be my good crisp edge. We're going to start working on the mandrel to hold the gear blanks. So we got our gear blanks, and we need a mandrel to hold it in the dividing head so that we can swap out the gear blanks and machine those. This is a piece of 1144 stress proof. A friend of mine, John at Encinal Machine, they have buckets of scrap. These are the drop ends of making Acme screws, and his boss is very gracious and generous, and he donates a few pieces to the cause. But if you haven't played with 1144 stress proof, it's really nice material. Super strong, machines like a dream. The only kind of negative, and it's a real minor negative, is you can't weld on it. But that's usually not a problem. But you'll see how easily this stuff machines, right? And the chips break. It's just it's pretty sweet stuff. Going the wrong way here. There's the feed. I think I'm going to go down to. Oh, we just gotta debark this thing. bad. So when we put the this mandrel in the lighting head, I moved a little bit. We're going to go ahead and indicate it in too. That's better. Okay. So on this end, we're going to turn it down to fit the gear blank, and then thread the end for a nut to clamp the gear blank on. We want a really nice fit between this and the gear blank. Oh yeah, that's probably pretty good. Okay. I'm going to thread the end. Oops. Butterfingers. Alright, where'd it go? Reach into the deadly chip pan here, full of all kinds of nasty stuff. Okay, close. So when given a choice, fine threads cut faster just because the thread depth is considerably shallower than coarse threads. I don't remember where I was. Alright. 44. Let's try 43. There we go. This might be enough. It's close. All right, threads ahoy. All right, I think we're pretty close now. All right, we're gonna finish up these gear blanks. We need a cross hole in them, so that's what we're doing at this point. I won't be able to use the mill in between, so I figure I'll go ahead and do the last bit that prepares the gear blank now, and then I can set the index head up and leave that in there while I do the whole thing here. Okay, that's pretty good. So I'm using the center line function of the DRO because I want to be on the center. So I pick up both sides. Then there's no math. There's no math or rounding errors or anything like that. It puts me right on center of what's there, regardless of whatever it happens to be diameter-wise. Now this one, I'm going to pick up on this side. Normally I would set this up the other way with the boss on the back, and the reason being I have a zero set all the time on the back jaw, right? So I know where it is, but it's not as good for filming. So those are some of the considerations for some of these kinds of things, right? Like I said, normally, so this is 0 and then 0 on that little stop, so I always can I can always pick up there. So all right, what's my number? Don't screw up. Let's see. Just a drawing there, Mr. Wizard. So it's a weird number, 111. 111. There it is. Okay. We're on center. All right, let's get a nice little center divot started there. And yes, I'm going to take that pin out real soon here. Let's get this out of the way. Okay. All right, let's get that out of there. Let's get the real Magoo here. So this is a wire drill, 999 diameter. So I'm crossing my fingers that it's going to drill a little bit oversized. So that's a bozo mistake waiting to happen there, is to bump the chuck into your nice part, because you choked up on the drill like you're supposed to. I saw somebody do that once. Alright, let's see what we got here. See if we're going to have to do anything weird. If I'm lucky. Kind of lucky. It's a little tight. Alright. I may have to lap that hole a little bit to get the pin to fit the way I want it to. That's pretty. Not quite though. All right. All right. You know what? I'm gonna take that out, and I'm gonna go ahead and drill the other one, and then we'll deal with that hole separately. We're gonna lap this hole so that it fits this 100 thousandths pin, and what I'm going to use is this is called a needle lap, and this is copper and it's split, and you can resize these with a little tool here in the slit to expand them so that they fit snugly. This one fits pretty good actually. So we're going to go ahead and use that. And then we're going to put a little bit of diamond schmoo on there. And get the lid off. There we go. This is a 12 micron diamond here. Should I do this by hand? I think I'm going to power do it, but I'm going to be conservative. I'm only going to give it a few strokes, and then we'll try it here. Now, the hard part, getting it in the hole. You see it changed. The stuff changed color. Let's get that out of there. All right, it's kind of starting, so let's give it a little more English there. There we go. Okay, that's good. All right, well, that worked pretty good. Let's do the other one, and then let's cut some teeth. So first off, we're going to set this thing for our angle, our helix angle that we measured earlier, which was 31 degrees. So these little Ellis heads are kind of neat because they have an angle scale on the top, and they're real easy to set for angles like this. Kind of snug it a little bit, and then get my magnifier, since I'm old and blind. Yeah, it looks pretty tasty there. Snug that up. And then what we'll do is we'll put our arbor in here, and then we're going to indicate the arbor. And I'll show you how to release this and freewheel the chuck, and so that makes it easier to indicate. So there's two screws at the top here, and it's kind of not obvious, but this allows you to disengage the worm. As you see, I can loosen these up. I think they push on the shaft, and let's see here. Yeah, okay, that's what I want. So that disengages the worm, and this makes this easier. Let's get a little indicator in here, and then I want to I'll check and make sure that's still in frame nicely. Come up a little bit. Go that way, that way. Can you guys see that? Oh yeah, you guys can see that. Okay. All right, so let's start there. All right, so that's a low. So this is not like a normal 4-jaw because it's a buck adjust through chuck. So low. So I want to push this way. Oops. Probably made it worse, yeah. Okay. The other way. So I moved the indicator around to the top, and this has made it a ton easier to adjust instead of trying to do it off of the side and the back. So I can see the screws and everything. So we're pretty good now. I don't know, half a thou or something like that by the indicator. So I'm going to re-engage the worm and then mount the gear blank, and then the involute gear cutter, which I haven't shown you yet, I don't think. That's this little monkey right here. And then there's some calculations so that I can, because we're at an angle, I want to be on the center line of the gear blank when I come in this way, right? So there's some math involved in that, and we'll go through that part. Okay, so here's what we're doing here. All right. So this is our gear blank here, right? And what I want that, so the involute cutter is coming through at this angle here. And what I want it to do is I want it to intersect the center of the gear blank, okay? The center of the shaft and then the center of the width of the gear blank. So I want it to pass through that point. So this number's important. And here's how you derive that. And I just laid this out in CAD real quick to make my life easier. But anyway, here's the math behind it, right? So we know we're tilted at 31 degrees, okay? And we know the diameter of the gear blank, which is that. So half of that is this number here. And then we also know the width of the gear blank, which is that number. So half of that is this little triangle here. So now what we can do is we can figure out what that hypotenuse is there of that little right triangle, okay? And then we can figure out the angle, okay? And then we know that the total angle is 31 degrees, so whatever this angle subtracted from 31 is the remainder, right? So we know the hypotenuse of this one, which is also the hypotenuse of this other one. And then with the angle and the hypotenuse, we can figure the length there. So that's kind of how that all works out. So the reason I need that is because this corner is the only thing I have to touch off on, okay? And you know, I don't have good access to the shaft. I don't have good access to this point here in space, right? So I need to use that and, you know, literally subtract half the cutter, okay, and then move down, and then my cutter will be right on the right on this center line here. So anyway, that's what that's what we did, or I did, and that's what we're gonna do over at the machine, and then we're gonna cut some teeth on this, and then the next problem that comes up is measuring how deep to cut the teeth. So we'll go through that in a minute too. So here's the latest insult: is I can't quite fish this in here to reference this surface here on the gear tooth cutter. So what that means is, what I think I can do, and let's try it here, is put this in back here, take this off, and that surface here, right here where it's touching the arbor, is a good 0 in this case. This is not my favorite arbor. This is a jeweler's saw arbor, and but this has an oddball hole diameter. Okay, so that should work. Let me get on center there. Come over, and this should be pretty pretty good. Yeah, and I can get in there. All right, so I'm going to come in. All right. Okay, touch off. Now I got to make sure I go the right direction. So I zeroed the quill DRO now. And that's the top surface of the cutter. So I need to come up half the thickness of the cutter. And that cutter is 200 thousandths thick. So I'm going to come up 100, 80, 90, 99. Okay, right there. All right, and I'm going to zero that little sucker so I don't lose track of that. Okay, now let's put this back on like that. This is when you need 3 hands, right? So this little arbor has a kind of a spring-loaded cone in it. Annoying cone. All right, I think I got it started. Come on, get in there. Okay, that's pretty happy. Now tighten this up good. I got it in back gear, so okay. No slippage. Okay, so this is the index part of the index head, and so there's a known gear ratio through this, and it's 40 to 1. So 40 turns here is 1 turn here, and some clever guy a long time ago figured out how to do fractions with hole placements, which is kind of interesting. So we have a 23 groove, and I'm going to call it groove because that's what we're cutting. We're cutting grooves. And for 23 grooves, it's 1 turn and 17 holes. So what we do, there's a movable sector plate here, and this masks off 17 holes. So 1 tooth is going to be 1 turn plus 17 holes right there. Okay, and then so that was 1 tooth index, and then I bring this around again so that I don't lose my place, and then I do 1 turn and 17 holes. Okay, and you keep going around and around 23 times, right? And that's how you do that. And so there's different plates that come with this, and let's see if you can see it here. So here's the numbers of holes on the bolt circles, and in this particular case we are on the 23 hole circle of this plate. Okay, and so I want to start at the very top. I usually like to start at the top, make sure I set my sector, and then the other peculiarity that people get screwed up on is you look it up in Machinery's Handbook or wherever, and it'll say 1 turn and 17 holes, right? Well, they don't count the hole that you're already in, okay? So you need to have 17 clear holes, okay? 17 clear holes, not counting the one that you're already in. So other people, it's not like they tell you that, okay? So you just got to learn the hard way, right? So if you do small numbers of indexes that become, or small tooth counts or groove counts, then you kind of see it because you're off, right, when you go around. And although it doesn't explicitly say it anywhere. So anyway, that's the deal. All right, so we're ready to cut. Let me get the camera at a good angle here, and we're just going to go to town on this thing. The last thing I wanted to mention is this is how we're going to determine the depth. We have a good gear and we have a worm, so when those are in mesh, we're going to measure over that whole mess, and that's how we're going to very carefully determine what the, in fact that's the number I keep getting, 1 inch 7/28. Between the 2 gears, that's what I've been getting, so as I check this. So that's going to be our target number. In fact, to write that down on my handy pad here. 1.728. All right. Contact. Now, how much to go depth of cut? I'm already zeroed. Get up there. It's a little fast. That doesn't seem bad. Move this stuff out of the way. Fill up the chips. Oh, that feels good. So I think I can be... I'm trying to determine something that is not a wimpy cut, so I don't have to make a bunch of revolutions here. Good. Alright, so that's going to be my number, I think. So I got to be a little bit careful here. I want to make my index movements with the cutter that way. So one turn and 17. Move the sector wheel and let's go. Next tooth. Oh yeah. So I got my hand on here just to feel for any vibration or anything icky. Anything icky happening. And it felt okay to me. One turn. 17 thousandths. Or 17 holes. Not 17 thousandths. Okay. We're off and running. It's starting to look like a gear, so we're going to take a measurement very carefully here. Oop, trying not to bang that camera there, Mr. Wizard. So inch 748, 747. 747. Yeah, okay. Let's do that again. 43. 43. Yeah, okay, 743, 744. Alright, so what was our number? So what is that? 1.743. 1.728, that's our number here. minus 15 thou. Okay, now since we're measuring over the OD of the gear and the depth on one side, right, it's going to be a radial movement, so we're going to come in 15 thou this way towards us here, or put the part into the cutter 15 more thousandths, and that should give us our depth. Tooth form looks pretty good. They're nice and parallel all the way down the length. And the only thing I don't like is it doesn't have a chamfer on that side of the gear, but we can fix that later, easy. So let's we're gonna go in another 15 thou. I'm just gonna go right to my number. And I'm gonna lock the what's going on here? A bit like that. Okay. Alright. So I think we're ready to go again. Let's see what a 15 thou cut. I'm going to speed it up a little bit. Okay, we're on the index that we started on. Finish looks pretty good in there. Let's give this thing a whirl and see what we got. That's good. Let's see here. Oop. Did I knock that out? Yeah, a little bit. Okay. Still turns. All right, no play. Oh yeah, look at that. Yep. All right. Let's, should we power it? Why not? Oh, look at that. Sweet. Oh, you know what we can do? We can ink the teeth and see how the worm is hitting those teeth. So that might be a fun thing to try. And I can also lap these together to get them to run real smooth too. Although this isn't the armature that'll be used with this gear, so maybe it doesn't matter. But let's ink that and then see what that looks like. All right, I got the gear inked, and there's my proof. All right, let's run this thing. Put a little pressure on it. What do we get? There's a fair amount of pressure. Let that run a few cycles. See what it looks like. All right, well, I think that about wraps it up. So the last thing I was doing there was I had inked the gear. Well, the contact is way down at the bottom, and it's not an ideal, it's not even close to ideal contact pattern between the gear and the worm. And that's because this is a simulated helical gear. And now, the good news is I think it's going to work fine in that this is hardened steel and this is hard bronze. So these are going to work together and until they they're going to seat. And you can see that this material yielded. So I have pretty high hopes here. But my friend Will's wife's going to test this out for us and see how it works. Anyway, that was kind of fun project. Thanks for the head scratching there, Will. And we'll give it to him, and hopefully another loaf of bread will be forthcoming. Hint, hint. Not so obvious. And and then maybe if it works pretty good, then maybe I'll make some that are truly helical, with using the little Buildexer helical indexer, so which I don't have right now. It's getting some upgrades right now. So anyway, thanks for watching. I hope you enjoyed that. I had fun making that, and I'll see you next time.